Hi, how you doing? So I'm doing this for one more semester because, well, not just, I might do it a third one, we'll see. But yeah, this is season 2, if you didn't know what the S2 stood for. And the first episode of season 2, because that's the E, or is it E on your side? I don't know. But yeah, this is my little chem tutor thing. And I did this first time last semester, and it seemed to go okay. There's some things that didn't go so okay, but I figured I'm going to keep all of the old stuff up on YouTube, because why not? There are worse things on YouTube. We're starting off looking a little better and sounding a little better because season 1, episode 1, I had a older webcam and I wasn't using my mic here. So I think we're a little better. I'm still using Google Hangouts because that's the cheapest way to do it. I made $1 from all those little ads at the bottom last time. So yeah, that didn't buy capture software. That's okay. I'm doing it for funsies most of all. So this one's going to be relatively short because the semester's just started. So there's some really intro stuff, and I've done a few other videos on some of the more involved stuff like dimensional analysis and the like. So for the first one, just to get the rust off over the summer, and to do it quick because I'd really hate for the internet for something to crap out on me. We're using Windows 10 for the first time, so let's see how it goes. But for general one, folks, we're going to do a little bit of sig figs, significant figures. Even though the thing about sig figs is that as the semester progresses, they really become less and less important, at least for me. I mean, there are some instructors, it's like they are sig fig police, and your instructor may be that way, and that's the way it is. I may be a police about other things. I am kind of deadlines. I'm kind of really tough on that. But with sig figs, you know, that's the first thing people tend to stress out over. Although, yeah, we got bigger fish to fry as the semester goes along. So the main thing to worry about with sig figs, I guess, are the zeros. Because if you see a number, actually back up a minute. When you're actually making the measurement like you do in lab, you know, however many sig figs you record is how many you see. So for example, if you're measuring mass on a balance, then it's depends on how many digits your scale can go out on. If you got just a cheaper 1 decimal place balance and your sig fig only goes out to the first decimal place. If you have one of those more expensive balances and go out to 4 or 5 decimal places, then sig fig's all about certainty. The more decimal places you have, the more certain you are about your measurement. But on the lecture side of things, the way it works is somebody's giving you numbers, usually in a word problem or on a data table, and you have to look at those numbers and tell whether or not they're significant. And the problem mainly comes with, like I said, with the zeros. Because if it's not a zero, then you're assuming those numbers are significant. The trick is knowing when zeros are significant and when they're not significant. So, is that my? I got both open. I think this is it. Yeah. Actually, nope. Yeah, here we go. This one. Full screen. All right. So, no, actually, it's general too. Should label my files better because I just got this big thing. That's it. Hey, third time's the harm. All right, so again, the X's represent numbers that aren't zeros, but zeros can either appear in front of the number, in between other numbers, or at the end of the number. So the ones that appear at the front of the number, what people sometimes call leading zeros, those are never significant. Never, never, never. And we'll kind of see why in a minute. Ones that are in the middle of other numbers, those are always significant. And we'll see why in a minute. The ones at the end, those are kind of conditional. Generally, the way I like to do it is that they're only significant if there's a decimal place. If you don't see a decimal point, you assume that the ones at the end aren't significant. Again, for reasons we'll see in a minute. So looking at a few examples, let's see what I mean. Take the number 623. No zeros there, so we're assuming all those numbers are significant. So we got 3 digits, 3 sig figs. But let's say you have 0.00623. Remember, the ones in the front are never significant. You see a decimal point, that's not for the ones in the front. Those are the ones at the end, are trailing zeros, as people sometimes call them. I don't think I called them that before, but I pointed out leading. So again, ones at the front are never significant. And the reason they're not is because when you convert to scientific notation, they go away, because the leading zeros, they tend to just be placeholders. Now, we needed those zeros, 2 zeros after the decimal point, so we could put that 6 in the 3rd decimal point. What is that, millionth? Yeah, millionths place. So yeah, that's why the ones in the front are never significant. They're just placeholders. But let's say you have 0.6023. Again, the ones in the front are just placeholders, but the one in the between the 6 and the 2, that's not a placeholder. All right? And you can kind of see that when you convert to scientific notation. Now, that 0 doesn't go away because it's not a placeholder. It's part of the actual number. So that one counts in addition to the other 3. So now we have a total of 4 significant figures. So again, the ones in the front, never. The ones in the middle, always. What if you have something like 501,000? So again, 5 and the 1, they count. That 0 between the 5 and the 1, they also count, or it also counts. Those 3 at the end, though, if you don't see a decimal place, you can't assume that they're significant. I mean, they could just be placeholders. Maybe somebody rounded up to the thousands place. It was 500,900 and something, and they rounded up to 501,000. There's some ambiguity there, and ambiguity means uncertainty, and sig figs are all about certainty. So if you're not sure about those zeros, you really shouldn't count them. So we will say 3 sig figs. And I messed up. That should be 5.01. Oh, I'm off to a good start this so far, aren't I? So I wonder if I can put that in and it show up. There we go. But let's say whoever wrote that number, or let's say you were recording that number down in your own data table, and you want to make it sure that those zeros aren't placeholders. The number actually ends in 1,000. Well, in that case, you want to add a decimal point. Whoever is showing you the number should add a decimal point. And we usually do it by 0.0. You can add just a decimal point without the 0, but most people don't because it looks like a period. All right. So we have we added another digit with the 0, but that's okay. It's just part of the number now. So again, the 5 and the 1 count, the 0 between the 5 and the 1 count, and now what's now 4 zeros at the end, they count. So that gives us a total of 7 significant figures. Oh, and I messed that one up too. All right, confessional I. There we go. There we go. Confessional, I actually made these slides like 10 minutes ago. Oops. And they were cut and paste too, so that was fun. So yeah, I wrote them in. I wrote the scientific notation to remind you that if you want to get rid of some of that ambiguity, you can always write it in scientific notation. That bottom number seems like overkill, but if you want to be really sure that all 5 of those zeros count, you can write it that way. And so now you have a decimal place there. You know, by definition, you're going to have a decimal point there in your number. And if you want to make sure that whoever reads that number knows that those zeros aren't significant, then yeah, you don't write them like we did up at the top here. So again, zeros at the front, never. Middle, always. At the end, only if there's a decimal point. Now, the one exception to the ones at the end, is a case where you have exact numbers. So for example, the metric system, that's an exact relationship. You have exactly 100 centimeters in a meter. So that means you have an infinite number of zeros after that decimal place. So we say it's infinitely significant. But you can't assume that a number is exact unless you're specifically told it is. You have to, otherwise you're going to assume the number's been rounded. And again, seems like a bit overkill early on in the semester, and for some people it is, for others it's not. However much you got to deal with sig figs really depends on who's teaching you, but their class, their rules. So again, remember, front never. I don't know what's front for you guys on the camera. Doesn't matter. All right, front never, middle always, end only if there's a decimal place. So another thing we can talk about just a little bit is, now that you know how to deal with identifying the number of sig figs, is, talking a little bit about the math. Do it again. And I did it right. There we go. Okay. So how you round when you're doing operations depends on whether you're doing addition, subtraction, or multiplication, division. So when you're adding or subtracting numbers together, you're going to find the number with the fewest decimal places and use that many. So basically, you're going to round to the common decimal place or numeric place or place value, whatever the math folks are saying. I always say decimal place just because I always say it. But for example, let's say you're adding these two numbers together, 12.5 and 0.384. The number you come up with is 12.884. But the answer you come up with on a calculator, although this one you can do in your head, isn't always the most accurate answer. So with addition and subtraction, again, you're going to round to the common decimal place. In this case, it's the first decimal place. So we're going to round to 12.9. So again, it's all about uncertainty. After that 5, we don't know what comes after that because we only measured to the first decimal place. If they're both zeros, then yeah, it's 0.884. If it's anything else, it's not 0.884. So again, you're not sure about those last two digits. And again, sig figs is all about certainty. So we really shouldn't include them in our final value if you're being picky about sig figs. If you're multiplying and dividing, you're going to go by significant figures. Whichever number has the fewest significant figures, you're going to round to that many sig figs. So if you're multiplying these two numbers together, your answer on your calculator is 0.0387156. But again, there's some uncertainty in some of these digits. It's similar reasons to the question marks I showed earlier for the addition problem. But to show you the question marks and the multiplication, I'd have to do long multiplication, and ain't nobody got time for that. I believe Harriet Tubman once said that. But actually, Rosa Parks would have been a better one. Anyway, so we got the number at the top has 5 sig figs, no zeros in that number. The number at the bottom only has 2 sig figs because those 3 zeros don't count, only the 2 and the 1. So we're going to round our answer to 2 significant figures, which means we're going to round up to 0.039. And of the 2 operations you do, at least in general 1, the multiplication division one is by far the one you do the most. And that's because if you haven't found out yet in class, most of your math, especially for the first 4 or 5 chapters, regardless of what book you use, is going to be dimensional analysis, which I talked about in the start of the last season's set of videos, and also my old channel, General Chem Concepts. I did some examples there as well. And so for that, yes, pretty much just a long string of multiplication and division. So that's when you're going to use the most. But the addition and subtraction one might pop up every now and then. And you got to remember, for those guys, you go by the common, decimal place or place value. Yeah. So that's it for General 1 for now. General 2, we're going to talk a little bit about some things related to intermolecular forces. I talked about it a little bit last season. My microphone is off to such a good start. Yeah, at least I look better than I did last semester. Resolution-wise, not. Yeah. All right, so what's about? Oh yeah, intermolecular forces last season. So yeah, we talked about those a little bit. And for the first chapter that you're probably taking in General 2, which is probably the intermolecular forces chapter, yeah, IFs are the big thing in that chapter. So there isn't much more that I can talk about at this point for the Gen 2 guys, except maybe saying a little bit about how you use intermolecular forces to identify, who's got the higher boiling point or melting point, or some other properties that we talk about. I could talk a little bit about packing if you're in somebody else's class, but I don't talk about packing, cubic centered, all those cubic centers stacking. I have never talked about it, or I did try initially, and it just never really fit. And when you work at a 2-year school, I don't get a lot of chem majors, and they're the only ones who really would need it. And actually, I was a chem major, and I got that stuff again my sophomore year when I took inorganic chem. So I was like, you know what? I'm not going to talk about it. And I've been doing that for over 15 years, and nobody's taken my PhD away. Right. And I didn't, when it was time to write my book that I used for my class, which, if I was better at a plug, I'd have it ready, more handy. It's right here. Although it's not showing up, is it? Volume 2. I didn't include it there either. So I'm not going to talk about packing. I talked more about packing in the last 5 minutes than I have in the last 10 years in my own class. So moving on. So we're going to talk a little bit about how intermolecular forces can affect boiling and melting points. And again, I've got too much crap on the screen. Yes, nope, not that one. Not that one. What the hell? Yeah, Windows 10 is showing all these things that I didn't think I had open. Thank you, Windows 10. Bark, bark. Ain't it? Oh, it must not be open. Dun, 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 dun. Okay, there we go. Dun, 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 dun. Oh wait, I'm gonna get a takedown notice because I'll hum the Jeopardy theme song. Hopefully not. Where did it go? Is that it? Yeah, there it is. Okay. All right. So when you're trying to figure out, which substance has the higher boiling point or melting point, or some other things that you may talk about in the start of General 2, the first thing you're going to look at is intermolecular force. Right? Usually the stronger the intermolecular force, the higher the boiling and melting point is going to be. And for most classes, you talk about dispersion, dipole, and hydrogen bonding. And that's the order of increasing strength. Dispersion being a temporary dipole, more or less. It's the weakest of the main three. Dipole forces deal with permanent dipoles, so they are a little bit, they rank higher in strength. In hydrogen bonding, we said the thing that makes hydrogen bonding special is that it's basically a dipole-dipole force, but it's significantly stronger than the other run-of-the-mill dipole forces. If your class talks about ionic solids, then those guys would be next in line. They'd be the highest of the 4 in your case. But I only talk about these 3. So we won't worry about ionics. Right. So for example, I already said that. You compare ammonia with phosphine. They both have very similar, pretty much identical shapes. But ammonia ammonia's main intermolecular force is hydrogen bonding, because we define hydrogen bonding as a hydrogen bonded to a nitrogen, oxygen, or fluorine. And there's a nitrogen. Phosphine is polar, but it doesn't. Phosphorus isn't one of our 3 hydrogen bonding atoms, so it's just regular old dipole-dipole forces. So of these 2, we would predict ammonia to have the higher, the stronger intermolecular force, so it should have the higher boiling point or melting point. And if you actually look them up, yeah, ammonia's boiling point's around 240 Kelvin. Phosphine's a little lower, it's 185. So yeah, ammonia, the one with the stronger intermolecular force, does have the higher boiling point. Now, what if they had the same intermolecular force? Well, in that case, usually you can make a pretty accurate position going by which one is the bigger of the 2. And by bigger, you can either use molecular weight, molar mass, whichever you like to call it, or you can count electrons. Usually I use molar mass because when I see a compound, that's the thing I'm used to calculating. So whichever one is bigger, that one usually has the higher boiling point or melting point. So take your middle 3 hydrogen halides, for example, hydrogen chloride, bromide, and iodide. Of these 3, hydrogen iodide is the bigger of the 3, although I jumped ahead a bit. They all have dipole forces. But of the 3, hydrogen iodide is the biggest. It's got a molar mass of 128 grams per mole. And again, if you counted electrons, it would have the most electrons in the molecule. So of these 3, we would predict hydrogen iodide to have the highest boiling point / melting point. And if you look up either one, I'm doing boiling points because, I don't know, coin toss. Hydrogen chloride, the smallest one, does have the lowest boiling point. Hydrogen iodide, has the highest. And the reason that's true is because, remember, even though a molecule is polar, they still all have dispersion forces. So the bigger molecule is going to have more electrons, and it's going to lead to larger dispersion forces because you got a bigger electron cloud that's potentially causing these temporary dipoles. And for general chem 2, that usually works for most compounds. You know, look at IFs first. If you have to break a tie because they have the same intermolecular force, usually the bigger one wins. There is a pretty big gray area in the real world. I mean, you can have a really big nonpolar molecule, you know, this big. No molecule is this big. I don't know. A really big nonpolar molecule, and it'll have a bigger boiling point or melting point than a much smaller polar molecule, because the bigger molecule is so much bigger, its dispersion forces are just so much greater than that tiny little polar molecule's dipole forces, that'll lead to it having, you know, stronger intermolecular forces and stronger boiling points or melting points, or whatever else you may cover in your particular class, you know, like viscosity, surface tension. Usually the greater the intermolecular force, the greater those properties are. But again, it varies from class to class. All right, so I did a half anyway, I think. No, I didn't, because I started a little late, probably about 20. There's no clock here. All right, so yeah, there's the end of episode 1, season 2. I only screwed up like 3 or 4 times. It'll get better. It's first semester. So like 20 people are going to watch probably so far. So I'm not too worked up on it. But if you are watching and you're watching it during this semester, the year of our Lord, fall 2015. Yeah, 2015. If there's things that you want to see, then go ahead and in the comment section say, hey, in the future, could you look at such and such? And I will maybe do it. We'll see. Kind of depends on where we're at in the semester. Or you can shoot me an email. And if you're not in my class, it's rmarkmatthews@gmail.com. If you are in my class, then you already know my work email. Please use my work email. All right. Just so I can keep track of everybody. All right, so that's it. I will see you guys next time. And I don't know, Boomer lives.